Good morning. Welcome to today's webcast, From Capture to Storage, Enhancing Carbon Sequestration with Advanced Analytical Measurement. I'm Mike Rhodes, Managing Editor of Hydrocarbon Processing, and I'm your moderator today. As global efforts intensify to reduce greenhouse gas emissions, carbon sequestration has emerged as a critical solution for capturing and storing atmospheric CO2 to mitigate climate change. This webcast will spotlight Emerson's role in enabling safe, accurate, and efficient measurement solutions throughout the sequestration process. During this webcast, Emerson experts will discuss how their gas analyzer technologies and engineer solutions support precise monitoring during CO2 capture, transport, and storage. These solutions help ensure regulatory compliance, enhance operational safety, and optimize performance in carbon capture and sequestration, or CCS, projects. Joining us for today's webcast are Alice Fu, Senior Global Product Manager, Dr. Beth Livingston, Global Project Manager, and Keith Lindsley, Senior Global Product Manager from Emerson. Let's learn a little bit about our speakers today. Alice Fu is a Senior Global Product Manager at Emerson, and she supports the Rosemount gas chromatograph product line. She has been with Emerson for the past 20 years in multiple roles, including customer support, analytical system integration, product management, project management, business leadership, and currently in product management. Fu holds a bachelor's degree in biomedical engineering from Zhejiang University and an MBA from Shanghai Jiao Tong University, both in China. Dr. Beth Livingston is the Global Product Manager for the Quantum Cascade Laser Process Gas product line at Emerson. Beth holds a master's degree in chemistry and a PhD in physical and theoretical chemistry, both from the University of Oxford. Keith Lindsley is the Senior Global Product Manager for CEMS and Process Analyzer Systems at Emerson, and he has nearly 30 years of expertise in the process analytical systems integration industry, with a focus on business management, engineering design, fabrication, and the startup of complete continuous emissions monitoring systems. Lindsley has successfully implemented projects around the globe for the electric power generation, petrochemical, and other industries. He holds a Bachelor of Science degree in mechanical engineering from Purdue University. Okay, just some general housekeeping notes before we get started. Excuse me, following the presentation, we will have a short question and answer session. You can participate in the Q&A session by asking questions at any time during the presentation. Just type your question into the Q&A box located on the top left corner of your screen, then click the submit button. Please take the time right now to familiarize yourself with the webinar platform. At the bottom of your screen, there are multiple application widgets you can use. All the widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. The slides will advance automatically throughout the event. We have also included a couple of resources in the related content widget located at the bottom right corner of your screen. If you are experiencing problems with the program, please press the F5 on your keyboard to refresh the presentation. You can also visit the webcast help guide by clicking on the help button below the slide window. All right, we're ready to get started. I'll turn the time over to Alice.
Thanks, Mike. Hello, everyone. So this is Alice Fu. I work for Emerson as the Global Product Manager for Gas Chromatograph product line. So I'm very glad to have this opportunity today to talk about CCUS and how Rosemount gas analysis products and solutions can help customers to meet your measurement need. So first, what is CCUS? The first C is for carbon, here specifically for CO2. The second C is capture. We capture CO2 from those emission sources either before it enters into the atmosphere or after it is in the atmosphere. So after we capture the carbon, the next thing we want to do is to store them somewhere that out of the way permanently, so they won't go back into the atmosphere. And the third one is, other than just store them, as a waste, how about we utilize them? So anyway, there are all kinds of usage for CO2, both for industrial or for commercial products. Okay, so now let's take a closer look at the CCUS value chain. Value chain is just a fancy name, basically tells you a process from the beginning to the end. So it begins from, we capture the CO2. Usually we want to capture CO2 from those carbon intensive processes, or we call them heavy emitters, right? So those including refinery, chemical power plants, or natural gas extraction. There's a lot of CO2 produced. And also the most common one, the other one is combustion of those fossil fuels, gasoline, like we drive cars. So there are other processes also produce CO2, but these are the heavy emitters. So we capture CO2 from these processes, then we want to transport them. But in order to do that safely and efficiently, we want to purify the CO2 and liquefy them. So that way we can move a huge amount of molecules in a very efficient way. So the most common two ways of transporting CO2, one is through pipeline. We have a lot of existing pipeline infrastructure. We can utilize them, or we might have to build new infrastructures for that purpose. The other way transporting liquid is using the traditional vessels like ships, trucks, etc. So we transport the CO2 to a destination, then we either need to store them. We hear about sequestration. That means that we store the CO2 underground in the rock formations, so that way they will stay there permanently. And of course, we can use CO2 for other purposes. For example, like enhanced oil recovery process, we push CO2 downhole and we push the oil up. And other than that, we can directly use CO2 for food and beverage. I'm sure a lot of people like those drinks with bubbles, right, including me. And also CO2 can be used for many other uses by reacting with other composition. For example, we can use CO2 to make plastic. It can be used for making cement, speeding up the curing of the cement, and also even make urea, like fertilizers. Anyway, so this is the value chain summary. But through this value chain, there are a lot of measurement points. We need to know what's the composition of the gas, how much CO2 is there, and what are the impurities there, because the impurities might hurt your equipment, or pose risk to the environment and human health. So during the last few years, Rosemount has received many inquiries from different customers asking us to provide solutions to measure the CO2. So this chart looks very busy, but don't worry about those little numbers. Basically, it just shows a snapshot that there are customers all over the world. They have need to measure CO2. We put those requirements together. So on the left side is the components that they want us to measure. And on the right side, it's the levels, concentrations of these components. So we just look at this. The impression is a lot of customers need CO2 measurement, but their measurement requirements vary greatly depending on their process. And among these components, usually there are hydrocarbons, there are moisture, SOx, NOx, and those light gases, like we call permanent gases, like nitrogen, argon, helium, etc. And there are also sulfur components, there are CO2, of course. So, and you look at the concentration level, it can be very low down to ppm level, can be very high, almost all the way up to 100%, right? And so you can see each CO2 measurement requirement is different. They have similarities, but no two are identical. So basically, this requires very complex analytical measurement solutions, not necessarily very complex, have to be tailored for each process and each application. So with that in mind, let's see how Rosemount gas analysis can help on that. So as a GC product manager, I would like to talk about GC first. So chromatograph, it is a Greek word actually means color writing. So you might still remember we did this experiment in middle school, I think, in the chemistry class. The teacher brought in a bottle of black ink and he said, I'm going to show you a magic. So then he dipped a few pieces of white paper, they are very absorbent one, into the ink. He said, just wait for a few minutes. Then after a few minutes, we see those different color bands form on those white piece papers. So as a kid, I said, how come black ink is black? How could you see different colors? So the teacher explained, black color is a combination of the rainbow color pigments. So the reason you see them on the paper is because when they travel through the paper, some pigments travel faster than the others. So this experiment vividly showed us that a mixture of compounds, they can be separated by the difference in how fast they move through a specific medium. This simple experiment actually tells the GC principle. It is separation and detection. In the GC measurement, we separate the physical components in a mixture and then send them through the detector to be counted to determine the concentration. So let's see a very simple basic chromatograph system. So in the real world, the chromatograph system can be simple, can be very complex depending on the application, but doesn't matter or who makes the GC. Each GC system usually always have these three parts. So from the left to the right, on the left side is a sample conditioning system. So GC is not an in situ instrument. It's an extractive kind of measurement principle. Basically, we take a sample, extract it from a process, condition it in the sample conditioning system. So basically, we filtrate all the particles, the mist out. We want the sample to be in single vapor phase, clean, dry. We adjust the flow rate, adjust the pressure, so that way the sample will meet the analyzer requirement. For Emerson GCs, most times we require the sample be at 15 to 20 psi. So after this, the sample gets injected into the GC oven. Of course, the oven is heated, right? We bake cookies in the oven, but not in the GC ovens. So inside of the GC ovens, there are three critical components, analytical components. One is the valve. The job is to inject the sample and direct them through the columns. And the column is where the separation happens. The column is a very long piece of tubing packed with chemical compounds that's designed to separate the components in the mixture. And after the components are separated, we send them through the detector where the concentration of each component is counted. So after this heavy lifting is done in the oven, all these information gets sent into the controller. Controller basically where all the reports are generated, all the calculations are done. Also, the controller controls the oven, the GC works operation. So anyway, all these three parts work together as a system. So if we compare them with the human body, the sample conditioning system is like our circulatory system. Take things in, push the thing we don't want out. The oven is our heart. When the heart is beating, we are alive. We are full of life. Controller is our brain, does all the calculation and the thinking, right? So they work together, form a system. So, okay, now we know how GC works. Let's look at what type of products Rosemount offers. So in summary, we have three different type of products. If you look at the picture in the middle, from top to down, it's 470XA, the smallest one, designed for relatively simple applications for both natural gas and renewable energy measurement. And the one in the middle is 700XA. It's a little bit bigger, so it can do more complex applications, can fit in more hardware. And the one on the bottom, the 1500XA, it looks like a refrigerator. It's the largest one, more heavier duty GC that you can put even more hardware into it, so it can do more complex applications. So they are designed for different types of applications. So if you look at on the left, this table, the measurement table, is specifically for the CCUS type of applications, where the CO2 and all the other impurities need to be measured. So this is the list that the GCs measure often. Doesn't mean these are the only components the GCs can measure. These are just the components we see over and over from the different customers' requirement. So if we just take a look, GC can measure all sorts of hydrocarbons, including methane, ethane, propane, all the way C9, C10, etc. We measure those light components, we call inert gases like argon, helium, nitrogen, and we can measure oxygen as well, CO, and different sulfur species, H2S, COS, mercaptans, formaldehyde, formic acid. So this basic tells, so just want to make sure we say GC can measure these, does not mean one GC can measure all these. It really depends on the applications. Sometimes you might need more than one GC to measure all these components, right? So let's look at the strengths and the weaknesses on the right side. First, the GCs, Emerson GCs, and a lot of other GCs, they commonly utilize three types of detector technologies. One is the TCD, it's the thermal conductivity detector. We call it universal detector. It can measure almost everything that GC can measure. It can measure low level down to ppm, high to percentage, and the strength, especially compared with other technology, it has the best lowest detection limit on those inert gases like argon, helium, nitrogen. And the second detector technology is flame ionization detector. It's a specialized detector. It measures those very, very low level of the hydrocarbons. When the TCD detector is not sensitive enough, ppb to low ppm level, FID comes into play. And it also measures the low level of CO and CO2 with a methanator. And the third type of detector is flame photo, FPD, FPD photo, okay, I forgot the brain fat, sorry. FPD detector measures trace sulfur, very low level, ppb to ppm level, flame photometric detector, so including H2S, COS, and mercaptans. So those three work together, they can measure a lot of components. But as a technology, it does have its weaknesses. For example, when there's both argon and oxygen present in the same sample, we cannot, common GC columns cannot separate them. So we can only measure them as a combined output, like argon plus oxygen. If you have to separate them, the other solution is you have a separate oxygen analyzer, which is very, very affordable, and there are all kinds of technologies in the market. You use GC, measure argon plus oxygen, then you use the oxygen analyzer, measure oxygen, then you compare the two numbers, you calculate to get argon. And GCs can measure water, but it's not very good. The lowest detection limit is not low enough. Also, it is really difficult to get a calibration gas blended with moisture, so it's very hard to calibrate it. So usually, most customers just use other technology to measure water. And also, the GC measurement, as we talked about, it's an extractive type of technology. Take a sample, measure it, then you inject another sample. So it takes minutes, depending on the application, can be 2 minutes, 5 minutes, 10 minutes. Compared with continuous gas analyzer technology, those take seconds, right? So this is about GC. So now let's see, how does GC work for the CCU application? So after collecting all these different measurement requirements, we overlap them, analyze them, say which components are always required for CCU applications. So we narrow down to the list, on the left side. Usually customer want us to measure methane, ethane, C3+, and there's always, very commonly, there's hydrogen, nitrogen, and obviously we want to measure CO2 directly, right? So these are the components almost every customer asked. So we developed an application. We standardize it so that way we don't need, customer can just get it off the price book. So this application is very, very suitable for CO2 custody transfer process that we are very confident it's going to boom, because the CO2 have to be captured, then transported, and then get stored. So during that, there will be a lot of handover custody transfer from seller to buyer. And for custody transfer type of measurement, the most critical thing is you have to be accurate. The metering skid, the uncertainty has to be low. That way it's accurate because it's a cash register, right? The measurement result is used to send bills. So of course you have to be accurate, reliable. So in order to lower the uncertainty of the metering skid, the full composition of the gas needs to be measured because we need to know the mass of the the density or the mass of the gas. So we need to measure the full composition. And for full composition measurement, GC technology is the most suitable technology, which has been commonly implemented into the natural gas custody transfer. So CO2 custody transfer will have a lot of similarities with natural gas custody transfer. So we developed this standard application on our Model 470XA GC. That's the smallest one. It's small, it's nimble, it's cost effective. And you can see the comogram on the bottom. All these each components has a peak, and how the size of the peak is directly proportional to the concentration of the components. And it takes about 5 minutes for each cycle. And the repeatability of CO2, that's the critical component, is very good, plus minus 0.1% of the full measurement range. And as soon as we rolled out to the standard application, it was very well received by our customers. So here, I'm just going to show one successful example. So if you look at the two pictures, this is a US, the very well-known or key petroleum company. So they got permission from EPA to build those Class 6 wells for CO2 sequestration. And Class 6 is the highest class, right? So the picture on the left is that pad. That's the first well they are going to drill on that pad. And on the right side, the picture is their CO2 capture facility. They capture CO2 directly from the air. So their process is they capture the CO2 from the air, and they are going to transport the CO2 to the site with the well, and they are going to push the CO2 down, store it into that well. So the process is CO2 sequestration. So the customer came to us, they said, oh, this is our first project. We don't have previous experience. And because it's direct air capture, the funding is really depend on the government, right? You have to get carbon credit, show them how many tons of CO2 we are going to sequestrate. So they get money from the government. So the funding is limited. So you need the whole project to be low cost. So they need a solution that's effective, but low cost. So the CO2 measurement is critical. That's the money counter, right? So the accuracy, they require plus minus 0.25. But other than CO2, they also need the trace oxygen and the moisture to be measured, because those components may damage the well material, right? So with this, they came to Emerson. The reason they came to Emerson is, they used Emerson GCs many times for their custody transfer in natural gas and hydrocarbons. They trust and are confident with Emerson's experience and expertise in custody transfer. So they asked us, do you have a solution for CO2? Okay, so we told them, yes, we have such a solution for you. Not only we can meet your requirement, exceeds your requirement. Our repeatability is plus minus 0.1. You are only asking for 0.25. Also, we have the 8 weeks, the best lead time in the industry. So our system integration group packaged the whole system, gave them a turnkey system to measure not only CO2, also the oxygen and the moisture. And this was delivered, and the customer is happy. So I hope this application is also helpful for you. Anyway, that's what I have for the GC portion. And now I'm going to hand it over to my colleague Beth, talking about the continuous gas analyzers. Thank you. Beth?
Okay, thanks very much, Alice. So my name is Beth Livingston, and I'm the product manager for our laser-based products at Emerson. So whilst Alice has been talking about our chromatographs, I want to cover our continuous gas analyzers, and these fall into two product families. We have our laser-based products, which some people may be familiar with as being called QCL products, and we have our process gas analyzers, or our PGA product line. So to start with, I'd like to talk a bit about our PGA products. So PGAs are a more traditional technology that people might be familiar with for gas analysis. And these analyzers use a mix of different technologies to meet customer measurement needs. Typically, we can include NDIR, which is a technology suited to measuring gases such as CO and CO2, electrochemical sensors, which are ideal for low-level detection of gases like oxygen and H2S, thermal conductivity, which is suited to measuring inert gases such as hydrogen, and then also paramagnetic detection, which is used for targeting percent levels of oxygen, for example. And finally, chemiluminescence detectors, which you would typically see used to detect combined NOx measurements. So each of these different technologies has different strengths and weaknesses depending on what the application needs are. And the way that our process gas analyzers work is that we can use a mix and match approach so that you can pick the technology that is best suited for the measurement needs. So what does this actually look like in terms of carbon capture? Well, here we have our product family, which is the Extreme PGA gas analyzer series. And this comes in a variety of different enclosure options, ranging from our general purpose rack-mounted solution, the XEGP shown here, and right up to a hazardous area version of the Extreme, which is suitable for explosion-proof situations, the XEFD. On the left, you can see the measurement table. So this shows some typical gases that, as Alice has outlined, are crucial for carbon capture type applications, and what we can use the differing technologies for to measure these gases within carbon capture applications. And what you can see here is the key strength of the PGA product line is that versatility in its configurability, that you can use a variety of different benches to meet different measurement needs, and also achieve some of the lowest LODs for particular gases for impurity measurements within carbon capture. However, PGA, it's not as well suited for measuring LODs at low levels on inert gases, such as the GC can do. And there are some limitations in the gases that it can measure, such as formaldehyde and formic acid. So for these type of applications, we would propose a different technology or a different product family to meet those measurement needs. So what does this look like in some real world examples for PGA? So here we have a couple of installation examples where we've used our Extreme product portfolio to meet various carbon capture application needs. In this first application, this is where a customer was producing blue hydrogen. In this process, natural gas is taken through a steam methane reformer to be split into hydrogen, which then goes on for other industrial processes. And then also CO2 is a secondary output, which will then go through the carbon capture value chain that Alice outlined earlier. In this instance, what the customer needed was a single analyzer solution for multi-component analysis that could measure the impurities such as carbon monoxide, hydrogen, oxygen, and methane, and also the bulk measurement of the CO2 stream itself. So here, the Extreme product was an ideal solution as it was cost-effective, and it provides a continuous measurement of the gases so that the customer can monitor and control the efficiency of the steam methane reformer process. In our second example here, where we've had a successful story with our PGA analyzers, in this instance, this was an enhanced oil recovery process for a customer, or EOR. In this process, what happens is that waste carbon dioxide is taken from another factory or facility and is injected into the oil deposit underground to increase the underground pressure. This improves the efficiency of the extraction process. In this case, the CO2 was supplied from a nearby steel mill, very high pressure and relatively high concentration, but the customer still needed to measure that CO2 concentration within the resulting CO2 and natural gas mix at the outlet well to measure the efficiency of the EOR process. So in this case, an Extreme XEFD was the most appropriate product because this was a hazardous area location, and the CO2 monitoring in real time was achieved through this detection capability of this product. And you can see in the pictures there, we have the example of the site wells in the diagram there and how the process works for EOR, and also the installation of the analyzer on site in one of our cabinets as well. The second product family that I'd like to talk about in our continuous gas analyzer portfolio is the laser-based products. As I said earlier, sometimes you'll hear this referred to as QCL products because we often use quantum cascade lasers for our measurement of the different gases required for our applications. Now, unlike the PGA products, we have a single measurement technology in our laser-based analyzers, and we detect and measure the gas concentrations using direct absorption spectroscopy. Basically, this requires a laser to be shone through a small extracted sample of the gas and then onto a detector. The gas itself absorbs some of that laser light, and we can use the Beer-Lambert law to determine what that absorption means in terms of the actual concentration of the gas present. Our analyzers also use multipass cells, which means that we have two mirrors within them that reflect the laser light back and forth multiple times. By doing this, we can increase the path length of the laser through the gas cell and also increase our detection sensitivity of our products. The great thing about using this measurement principle and the Beer-Lambert law is that we can design our analyzers to be linear in response, and that as the only variable is concentration, the measurement does not drift with time and is very stable and requires minimal intervention and calibrations. Another advantage of the laser-based analyzers is that we can use different types of lasers, normally quantum cascade lasers and tunable diode lasers, and this allows us to access the mid and near-infrared region of the electromagnetic spectrum. This opens up detection of far more gases than is possible with just one laser type within a single analyzer system. It also means that the technique is very high resolution, which gives us good immunity to cross-interference and highly selective measurements. And the final feature of lasers in terms of their measurement capability that's worth mentioning is that they are very fast, with high-speed measurements of between 1 and 10 hertz typically. So that's a bit about how laser-based analyzers work. What does that mean in terms of their specification for carbon capture? So as with the PGA product portfolio, we offer a variety of different enclosures depending on application needs, ranging from our general purpose rack-mounted analyzer, the 5400 shown here, through to the CT5800 analyzer, which is our explosion-proof version of our laser-based product as well. The type of measurements that we can offer for carbon capture are shown in the table on the left for typical gases of interest. And as you can see here, some of the strengths are outlined for this detection capability, which is we can mix the different laser types of QCl and TDL to measure those different gases shown in the table. And we offer very low detection limits for these gases as well. However, there are some weaknesses to QCl and TDL-based measurements in that we cannot measure the larger hydrocarbons, so for example, propane or butane. And also, we are more suited to measuring smaller molecules such as carbon dioxide and carbon monoxide. So again, this just shows the different balance of the strengths and weaknesses for the technologies that we have throughout our product portfolio. So how do we use these analyzers in some real-world applications? In this first application here, where we've installed a laser-based product, this was where a customer had a gas processing plant where they were capturing CO2 for carbon credit. What they needed to do here was monitor the upstream methane that was leaking into the CO2 for quality purposes, and also monitor the water measurement, as water within CO2 can produce carbonic acid, which can damage the pipeline and equipment. So the ideal solution here, as it was hazardous area, was a CT5800 product, which could allow all of these gases to be measured within a single analyzer to the specification that you can see shown in the table here as an example for this application. Another application where we've installed our laser-based products. Now, unlike the previous applications that you've seen, this one actually only required a single measurement. So this is ideal for our CT4400 product, as this is a general purpose analyzer which is suited to 1 or 2 gas measurements. And in this example, the customer was taking the CO2 byproduct gas, and then they were injecting it into the well in a enhanced gas recovery process, similar to what we saw earlier for oil, but within a gas processing system here. And in a similar manner, the increase in pressure optimizes the end production well efficiency as well. So for this, they needed a high range measurement of CO2 up to 100%, and they also needed this to be combined with a flow measurement. So we provided a full system solution here with our laser-based CT4400 and an FB1200 for monitoring the flow as well. And this gave them real-time measurement for bulk gas monitoring in this combined solution. So hopefully, these examples of using laser-based and PGA technologies within real-world examples of carbon capture applications, along with the examples that Alice gave you for GC, show that there is a huge breadth in what is required for measuring in carbon capture applications. And as Alice showed earlier, there is no single standard that we're working to globally. There is a huge variety in customer needs and requirements. And a key outcome of that is that there is no single technology that can do everything that is required for carbon capture. So the Emerson gas analysis product portfolio is ideally suited as we have a huge combination of different technologies and different product families that we can pick and choose from to meet different customer needs. And hopefully that's illustrated here in this summary table, where you can see the different gases required for carbon capture measurements, how critical they are in terms of priority, some of the measurements that we are being asked to perform for carbon capture, and where you can use the 3 different product families of GC, QCL, and PGA to meet those measurement needs. Now, just to finish up before I hand over to Keith, this is the situation today for the Emerson product portfolio for gas analysis. We have these 3 distinct product families. But I am very excited because we have a new product coming, the QX1000. This will be launching soon. And the idea of this is to take this configurable ethos that we have of our PGA product portfolio and combine it with our laser-based product portfolio. So moving forward, there will be a new product family, which will take the laser-based measurement technology and the different technologies that we have in our current process gas analyzer portfolio and bring them into one single product to meet all these measurement needs. So please do watch this space for our future announcements on the QX1000. It's a very exciting time, and hopefully you'll be interested to hear more about that soon. So that's where I'd like to finish today and hand over to Keith, who will be talking about our engineered solutions.
Thank you, Beth. Good morning, everybody. I want to thank you all again for joining. I'm Keith Lindsley, Senior Product Manager for SEMS and Process Gas Analyzer Systems here within the Engineered Solutions Group of Emerson. So this is the segue into the Engineered Solutions offering for carbon capture, utilization, and storage. There are several technologies used to reduce greenhouse gas emissions, one of them being capturing and storing CO2. There are 41 commercial scale carbon capture and storage facilities currently in operation worldwide. An additional 26 facilities are under construction, and 325 are in various stages of development. In total, the project pipeline includes 392 facilities. I'll describe just one of them, designed, built, and supported by Emerson a little later in this presentation. So why are we in the integration business? Measurement Solutions Lifecycle Services is the Engineered Solutions Group of Emerson, or as I describe it, the integration arm of Emerson. What that means is that Engineered Solutions integrates and provides services for all of the analyzers, instrumentation, equipment, and software that we produce. We integrate these together in a complete package form, a solution to fill projects, max size and otherwise. Not only does that include Emerson products, but this also includes the other buyouts necessary to provide a complete solution, such as other measurement technologies, heaters, pumps, and other gas conditioned equipment. Our commitment to our customers is that we provide complete project certainty. That entails utilizing reliable, accurate, and best practice technologies into a project deliverable. As a trusted provider, we deliver low-risk project execution that are designed, procured, fabricated, tested, commissioned, and supported by a single accountability partner. Our 4 pillars, which ensures project certainty, contain utilizing best practice technologies, strategically utilizing our global solutions capabilities and expertise, utilizing and relying on our core engineering and project management experience and standards, and once that project is delivered, supporting the project with long-term lifecycle engagement. So here you see our portfolio of engineered solutions. In the top right corner, you can see our number, over 6,500 engineered solutions delivered globally from one of our integration hubs that we have across the globe. So in the 5 columns, these are really the solutions that we deliver into. The first 2 columns, these are the hydrocarbon custody and fiscal systems. The first column is the liquid variety. The equipment involved in those could be Coriolis meters, liquid ultrasonic meters, various types of instrumentation. Where these systems go are typically petrochemical, floating production storage and offloading, refineries, LNG, FLNG, pipelines, and utilities. That next column is also hydrocarbon, but now we're into the gas phase. So again, we're installing and designing Coriolis meters, gas ultrasonic meters, our gas chromatographs, and other instrumentation. And again, those industries include pipelines, petrochemical, FLNG, LNG, and et cetera. The next two columns are the analytical gas systems. So column 3, that shows our process gas offerings. So this is where the advanced analysis, chromatography and spectroscopy, these analyzers come more into play. As Beth described, this includes our traditional PGA analyzers and our more advanced quantum cascade laser spectroscopy lasers, as well as our gas chromatography. These systems typically go into selective catalytic reduction DNOx systems, gas purity systems, gas compositional analysis systems, as well as refineries. So the fourth column, analytical liquid and systems, more on the liquid and the wastewater. So these are the traditional transmitters and sensors that Rosemount manufactures. Things like conductivity, chlorine, ozone, end users, applications being steam and water analysis, wastewater quality, other municipality destinations like that. Then the fifth column is our sustainability and decarbonization systems, which include hydrogen measurement, CO2 measurement, and continuous emissions monitoring. Some of the analyzer technologies used there are Coriolis meters, our extreme PGAs, quantum cascade lasers, the Emerson data acquisition system, and various types of instrumentation. So again, those applications would include continuous emissions monitoring, CO2 capturing, hydrogen measurement, and biofuels measurement. So here's just a quick overview of engineered solutions and how we deliver our projects. So globally, we have a team of over 700 people dedicated to the design, fabrication, the testing, commissioning of the entire system. So if you look at the columns there, in the blue pre-feed, the blue feed and pre-feed areas, this is where we get our engineers, our global solution architects for early concept of operational success. This is where our input, we set the expectations of improved ROI for the end user. The next row would be that detailed design. We have application expertise incorporating our best practices and design standards. This leads to meet budget expectations. The next line there is the execution line. So this is where we employ certified project execution. We have dedicated project teams who are SMEs in their fields, utilizing project management tools that exceed the requirements of typical EPC projects, including the thorough documentation process. This leads to on-time completion for the end user. We then have the install and commissioning line item. So during this phase, we provide installation, commissioning, training, and a comprehensive handover, verifying all the KPIs that have been met and achieved. And then finally, we have our lifecycle services offering. This is where we have the compliance management, the digital asset tagging and testing, and our complete handover. We have here in Houston, here in Pasadena, Texas, we have one of our North American service hubs where we store parts, operate a service depot, and conduct FATs. An Emerson system will lead to a long-term analyzer system performance and lower life cycle costs. So components of this slide were covered earlier, but I'd like to emphasize the importance of some of the various elements. So understanding the phase change and properties of CO2, whether it be in solid, liquid, or gas phase, is important to designing and building this solution. Understanding so we can account for transportation in either liquid or gas phase with their temperature and pressure requirements. Understanding the potential for contaminants in the background of the sample, we have to know this, have to know what those impurities are within the CO2 stream because they have impact on the design and operation of the pipeline system. This all contributes to successful design and operations long after the system's been started up. So designing and operating near a phase boundary presents significant challenges for a measurement system, as small changes in temperature and pressure can cause large changes in fluid properties. So very, very important to capture all this detail in the design phase before we begin to construct. So when considering the challenges, regardless of phase, any change in pressure or temperature can lead to two-phase or multi-phase flow. Water needs to be removed as much as possible to prevent hydration, freezing, corrosion. Also, there's pipelines that are not capable of operating under the high pressure required for the dense phase. So here's that application that we provided in Australia. So this customer was looking to capture CO2 currently being vented to the atmosphere from its existing gas plant, again, locating in southern Australia. They are storing and sequestering over 1.7 million tons of CO2 annually. The gas is dehydrated, compressed, and transported through new or existing pipelines to be injected into the geological storage. The company's primary focus is to target net zero emissions by 2040. This project required knowledge of the local regulations and a consultative and a collaborative approach with the client to understand the standards and project specifications. To accommodate process conditions for the startup and operational phase, it was required to configure and design a high-pressure skid based on the Coriolis technology and the right analyzer solution for the CO2 mixture analysis, which in this case was our quantum cascade laser analyzer. This was built into an outdoor skid, not requiring a high-cost shelter or building. So this slide here, this slide represents just one of our systems that is installed in a typical climate-controlled building. It's Class 1 Div 2, has a Class 1 Div 2 safety rating. What you don't see here is the HVAC or the fresh air intake system that declassifies the interior of this building. Also, what you don't see are the sample systems, which are built just behind the analyzers on the outside walls of the building. This is done to conserve space and for safety considerations for the operators and the equipment within the building. There's multiple GCs and an Emerson Extreme Process branded gas analyzer in the picture. We can also see various sensors, transmitters, and with the computer workstation communicating with all of the equipment there, which then feeds on to Delta V or Ovation. This is my last slide. So this again is a very typical Emerson solution, an ambient environment exterior solution. So you see it's a rack system. The picture on the left, it's a rack system with a sun and a rain awning. Most of our analyzers at Emerson are built and designed to operate outdoors in ambient conditions, not requiring expensive climate-controlled buildings and indoor safety systems. Within that system on the left, you see a CT5100, and on the right, you see a glass-paneled sample handling system so that the operator can easily look in and see any gauges or whatever's happening within that sample system. On the right, say larger sample system box there. So it's a dual stream. You can see the four different, you can see the four heated sample lines in the top, 2 coming in, 2 leaving. This is in a more higher temperature hot box. So this might be going to a colder climate, either in Canada, northern US, or so forth. But again, meant to go outside. So that concludes my portion. Leaves us about 10 minutes here for conclusions and questions.
All right, we will now transition to the question and answer portion of our webcast. You can continue to submit your questions in the Q&A box located on the top left corner of your screen. We've had a lot of questions from our audience come in, so let's just jump right into these, if that's okay with you guys. Let's do the first question. Does Emerson manufacture TDLs for process heaters application for X's O2 measurement? Not quite sure what they mean by X's. It's possessive.
Okay, yep, I'll answer this one from what I think that means. But just to give an overview of our laser-based oxygen measurements. So correct, we do use tunable diode lasers to measure oxygen. We can use those in our CT5000 analyzers. We can offer oxygen measurement in sort of the percent levels that would be typical of continuous emission monitoring or combustion type applications. And another advantage of our CT5000 series for measuring oxygen is that we can do hot-wet measurements. So for applications such as combustion or emission monitoring, where you do want to keep the sample stream heated and not have to use complex sample handling systems, then it is ideally placed for measuring oxygen in that sort of 10 to 25% measurement region. So hopefully that gives you part of the answer from how I've understood the question. But please do look at the CT5000 product literature to see what our oxygen measurements are capable of doing and for what applications.
Okay, another question here. In the UK, early indicators are that FTIR technology is the preferred solution for these applications. Do you have any info on the weaknesses with this type of system against a GC?
Okay, Mike, so I will take this one. So I noticed Jeffrey asked this question. That's a curveball. So FTIR, I'm not an expert, but just a general understanding is the weakness of FTIR compared with GC is FTIR require very extensive sample preparation. GC also needs a sample system, but FTIR has special requirement. It's very high maintenance. That's what I heard from the customers who use FTIR. The second is FTIR has this interference issue from moisture and CO2, quite stand out. So if you are using this to measure CCU, it's definitely a disadvantage. Compared with GC, like we explained, the fundamental principle is separation and detection. We separate the components, so there is no interference. We eliminate that. FTIR cannot do that. Actually, it has peak overlap issues. So, like I said, I'm not an expert, but GC, like I explained, like for this type of CCU or other measurement, when you require it to be accurate, sensitive, reliable, like GC is very, very suitable. Like that's why it's very commonly the standard method used in natural gas custody transfer. So for CO2 custody transfer, we are confident GC is the better suitable technology. But I need to learn more about FTIR. So just use my answer as reference. Thank you.
And I just want to add one more thing to that. So whether it be our spectroscopic technologies or our GCs, within our spectroscopic technologies, we have multiple detectors. Our QCL technology, our TDL technology, and within our GCs, we have 3 different types of detectors within that analyzer. So FTIR, as the name infers, it's an infrared technology, and it is meant to be a multi-gas analyzer using the one technology, which is very useful. But one of the drawbacks that I've seen with FTIR that it is not as it's not as user friendly in backgrounds where the application is variable. So for consistent analysis for a process that doesn't change process often, it's very easy to build a chemometric model that measures values that don't fluctuate a lot. However, if you have unknowns, if you have a lot of fluctuation within that application, then the chemometric model needs to be more complex, and then that chemometric model probably needs to be changed and validated often, as opposed to simply just running known concentrations of liquids or gases like we do with our equipment. So I think that's a big part of it.
Okay. Another question here, and this may be referring to a number that you mentioned, Keith. Out of 6,500, how much or how many for sustainability and decarbonization systems?
Oh, that's a great question. So, within that number, Rosemount has been part of Emerson for more than 40 years. The way we categorize sustainability, we put SEMs into that number. I would say well over 1,000. So there's an awful lot of pipeline GCs out there, a lot of those type systems, but I would have to say over 1,000 of those Rosemount Emerson continuous emissions monitoring systems.
That's great. Here's another question from our audience. What are some common challenges operators face when integrating measurement solutions into CCS projects?
So a couple of things. So capturing a lot of these projects, we don't always have as much, or we don't always have as much information as we'd like about the process data, the process stream data. So one, getting as much of that process data up front in the design phase, even if they're outliers, even if we're accounting for components that we might not see often, depending on where these gases are coming from. So as much data as we can come so that we can design our system to account for all those contaminants, much less the CO2. On the other side is designing the system for the environment. So, designing for the tar sands of Alberta, much less the Gulf or the, in Saudi. So environmental challenges are a big factor. The process stream data, the other big factor, bringing those two together.
Okay.
May I add just a little bit? I think the other challenges is, like we already saw, the measurement of CCUS. There's no industrial standard. Everyone's process is different. Measurement requirements are different. And also we see that there's no single technology can meet all these requirements. So they have to evaluate different technologies to try to figure out which one is the best fit for this and for that. So Rosemount is here. We have a comprehensive portfolio. We have the expertise. We can help you to do that. So just like it's customized solutions, that's our system group is specialized in provide turnkey. So you don't need to go through that trouble. Just come to us. We will help you out.
Okay, sounds good. I think we have time for a couple more questions. Let's squeeze them in here. As CCS initiatives scale globally, what considerations should operators prioritize when they are designing or upgrading gas analysis systems for midstream carbon transport and storage?
I think that follows on nicely from Alice's point that we need to consider any emerging global standards. Yeah, so that would be my main thing, is what global standards or even regional standards are going to start being published that will dictate the measurement criteria that customers have to adhere to, and to try and give as much longevity in any installation so that we can meet those future regulations that might be coming in.
That's a very good point. I would like to add for midstream transport and storage, like said, they will need infrastructure, right? So if they can utilize the existing infrastructure, that will lower the cost, because all these big projects need a lot of budget. So usually always want to consider the budget. If you can utilize the existing infrastructure like pipeline, truck, ships, and also refer to proving and true type of measurement solutions in custody transfer, there's improve the certainty. So you don't need to reinvent the wheel. Go with the method that works and that meets the requirement and budget friendly. So I think we are here, we have a solution, we can help you.
Okay. We're going to push it a little bit longer today. We've got so many questions coming in from our audience. Well, let's squeeze in a couple more. Which are the analyzers offered in liquid CO2 metering skid?
So, okay, CO2, we talked about gas analysis. So all our analyzers want like the sample to be in vapor. And we understand CO2 will be transported in dense phase. It's really between the vapor and the liquid. So, but when we measure it, we do have to vaporize the CO2 to be in vapor phase. So like our system group, they design those sample systems, or they can work with external partners to design those sample systems that can safely vaporize the CO2 from dense phase to vapor phase. CO2 is a lot easier than LNG, liquefied natural gas. We have extensive experience dealing with those samples that needs to be vaporized. So for after the sample is vaporized, you can use whichever analyzer, depending on your measurement requirement. You can use GC, you can use our traditional process gas analyzers, or you can use laser analyzer. So really, vaporizing sample lies in the sample conditioning system. Our system integration group is expert of doing that.
Okay, and then this question is specifically addressed to Keith, although I'm sure the expertise of Alice and Beth are welcome, of course. Do you have a catalog of available engineered solutions customers can browse, or is each engineered solution custom and designed based on specific customer inquiries?
Both, right? So there are so many applications that we deal with. So many are custom, but we do many of them over and over again. So the ones that we know well, the ones that have that repeatability and success, we've built standard designs around. So the question was, do we have a catalog? So on our website, we certainly have a description and references to some standard solutions. And very timely question, because as we speak, we are updating. We are now updating and improving, how that looks on the engineered solutions website portion of Emerson. But feel free to contact me, and I'd be happy to share with you anything that the website might not easily.
Right. We also have a brochure of solutions overview is available in the related links as well. We want to thank our audience for attending today's webcast. Also extend a special thank you to Alice and Beth and Keith for sharing their expertise, and to Emerson for putting together this timely and informative presentation. Finally, an on-demand version of this webcast will be made available in the coming days and will be emailed to everyone. Again, to our panelists, thank you so much for sharing your knowledge with us. Thank you to our audience for your great questions and for attending the webcast today. We hope everyone has a great day.
Thank you, Mike. Thank you, everyone.
Yep. Thank you, Mike.
Thanks, everyone.
Bye.
Thank you.